All right, so today I will be showing you a small brief introduction as to how system calls are actually invoked inside OS 161, and from there we'll move on to how to go about actually implementing some of these system calls. Right? So this is where it all begins. So if you look at the file exception mips1.s, there is this one function written in assembly called common exception. And what common exception does is, this is the common exception handling routine. Or you can think of this as part of the interrupt servicing routines that are part of OS 161. And eventually, you can trace this down right somewhere at the bottom. It calls this function called mips_trap. Right? And thankfully, this is C code, so we can go through it in a little more detail. And mips_trap can be found in trap.c, found in that path. And what mips_trap does is it picks up the call number, which is basically the type of exception that occurred, and then figures out and handles it accordingly. So he checks whether the code was of type IRQ. He later checks whether the code was of type XSYS, and so on. So we want to pay attention to EXSYS because that is the system call exception. And inside this, what he basically does is he makes a few k asserts just to make sure that the interrupts are the way it should be, and then he makes a call to this function. And the argument that he's passing in is the trap frame. Now, what is the trap frame? I have explained this before. The trap frame is basically a structure that stores state of what the CPU, the state of the CPU before it got into this exception handling routine. So what is the state of the CPU at that point? Well, it basically consists of the state that the thread that was executing left it at, right? So whatever the thread was doing, that was what the state of the CPU was at. And because the thread made a call to syscall, it got here. And so he's passing in that state to this function. And syscall function is defined in syscall.c. And what syscall function does is it picks up the call number, which is basically an integer, and it switches on that call number. Now, as part of the code that you have been provided, there are only two system calls in place, systime and sysreboot. But we'll take a closer look at these two system calls to figure out how to implement the file system calls to begin with. Right? So, okay. So moving on here. So there is a case sysreboot, and if it is of type sysreboot, he just makes a call to this function, passing in a part of the trap frame, passing in actually one of the fields. And maybe I should quickly open up trap frame so that you guys can have a look at it. Anyway, while that's happening, he passes in tfa0. Now, what I can tell you is tfa0 actually is a field inside this struct trap frame that corresponds to a CPU register, which is termed as A0. So the MIPS architecture, this MIPS CPU has like 4 general purpose registers, A0, A1, A2, and A3. These are what you will use for argument passing, and each of these are 32 bits. So it gets tricky when you want to pass along 64-bit arguments, right? We'll take a look at that. Now, okay. So this is the struct trap frame. What it basically has is a field for every register that exists on the CPU. Not all of these you will use like often. Some of these are internally used, but the ones to pay close attention to are A0, A1, A2, A3, V0, V1. These are important, and also the stack pointer. Oh, this is also very important. This is the program counter. This is what stores the currently executing instruction, right? The address of the current executing instruction. Okay, so that's the trap frame. Now let's look at what sysreboot does. So if we quickly go back, you'll see that all these are of type unsigned integer, right? So it just stores an integer. Now going back here, we're going to see at what sysreboot does with this integer that was passed in. So this is sysreboot. It's found in main.c, I believe. Yes, it is. And so what sysreboot does is it takes in this code, which is of type integer, and does a switch on it. and depending on the type of code that was passed in, it handles it accordingly. Now, clearly there is a difference between what sysreboot does and what you guys are going to do, because sysreboot is like one-time execution, right? It's either going to power off or restart or something like that. It's like what I would call a hard interrupt, because that's the end of it. Whereas your system calls are more of soft interrupts, because it doesn't mean end of execution or a reboot. The kernel has to go on once it has finished executing that system call. So in this example, what we basically should pay attention to and what we should learn from is how to pass a simple argument to a system call, right? So the way this works is that there is going to be a user process that invokes reboot, right? And how does it invoke reboot? It invokes reboot by making a call to the C library which implements this function called reboot. Readable? Yes. So this is how the function looks. This is how the user process would execute reboot, right? So you just make a call to this function reboot and pass in a code. And those are the codes that are allowed, right? And what the C library does is it takes the argument, it puts it in A0, and then it invokes syscall with the appropriate number. Now sysreboot has a number associated with it, right? So that's what the C library does. So there needs to be a very good understanding between what is there in your kernel as the syscall numbers and what the C library also has as syscall numbers. They need to map. If they don't map, then the program thinks that it invoked reboot, whereas it might have actually invoked something else. So this is how a simple 32-bit integer is passed along. Now, time is a little more complicated, because let's quickly look at what the C library exposes as the time system call. Time, right? Okay. So the time C library function returns a value of type time t, but as arguments it takes in a pointer of type time t and another pointer of type unsigned integer 32, right? Uint 32. Now, if we jump quickly to the code here, you'll see that the arguments have been typecast to this type called user ptrt. And this is important to note, because whenever you're passing on pointers from user space to kernel space, they need to be typecast into this type. This doesn't really do much, but this gives a sense of understanding to your teammate and to yourself, because you're going to be writing a lot of code and you need to keep track of what is a pointer and what type of pointer it is, which is why this has been explicitly named as user ptr, just to denote that it's a user pointer or a pointer that is pointing to an address in user space, right? So what does systime do? So systime function is found in time syscalls.c, and so these are the arguments that it takes, and what it does is it invokes this function getTime, which is a kernel function, right? It invokes that function, it stores the result in two local variables, and then it calls this function called copyout. Now what copyout does is, okay, so the prototype of copyout is copyout, source, destination, and size, right? Copy from source to destination, and this is the size, the number of bytes that I want copied. So what he's saying is copy out from seconds. Seconds is the local variable, and then he's saying the destination is user seconds ptr, which is the user pointer that we passed in, right? And he's saying size of time t, and he's doing something very similar to the other argument as well. And so this is how you pass information from kernel space back to user space. Now what if you wanted to pull information from user space into kernel space? There is a equivalent function to do that. It's called copyin, right? It has similar semantics. There is a source, there is a destination, and there is a size. So now that we have seen how to pass in values and pointers, let's take a look at some of the system calls and figure out what they should look like, right? Let's start with open. So ignore the second function of open. You guys don't have to implement that. Pay attention to the first one, right? So open takes in a char pointer to a file name or the file path, and it also has some flags. Now these flags are actually very important, because the flags can be read only, write only, or read write, and there are some additional flags here as well, right? So what the flags denote is how to open the file, or what permissions to use while opening that file, So there are actually tests as part of the autograde. The autograder runs some tests to check whether the permissions that were passed in are correctly enforced. For example, it may open a file with read-only permission and then try to write to it. And your code should actually throw an error. There are errors. So if we take a quick look at write, you'll see that there are errors, right? So it should return ebadf because that file was not open for writing. So these error codes are very important, and you should make sure to return the correct error codes. Okay, so what does open do? So open takes in a pointer, takes in flags. Now how would that look in terms of code? It would look something like, first you would have a case, or I can actually type here. So it would look something like this, right? Case sys open, error equals some function. Let's just call it test open. You can call it whatever you want. The first argument was a pointer, right? And rule of the thumb is if a pointer is being passed in, it should be typecast to user ptrt, right? So I'm just going to say user ptrt of what? So the way the C library works is the arguments are actually passed into one of these registers, right? And there's a very simple ordering. The first argument, if it is 32 bits, goes into A0. The second argument, if it is 32 bits, goes into A1. And the same for the third and fourth. So the first question is, what happens if I want to pass more than 4 arguments? There is an explanation as to how to handle this. It's written in this big wall of comments. And basically what it says is all the future arguments past the fourth go into the stack, starting from stack plus 16, sp plus 16. So that's where all the other arguments end up. Now, that's not all, because what happens if I want to pass a 64-bit argument? Like Lseek, for example, actually takes in a 64-bit as one of the arguments to it. And the way this is to be handled is the registers in MIPS are actually paired, or they're called pairs of registers. Like A0, A1 is a pair, A2, A3 is another pair. And 64-bit values can only be split across pairs, right? So if I had a function called mySysCall, which was taking 3 32-bit arguments and then a 64-bit argument, I can't jam pack this into any of the registers because the first 3 go into A0, A1, and A2, and the 64-bit now can't fit into A3. So I ignore A3 and put it on the stack, right? And similarly, if you had a 64-bit somewhere in the middle, like for example, let's just quickly jump to Lseek. So Lseek takes 3 arguments, an integer, an off-t, and a whence. Now, we know the types of fd and whence. They're clearly int, right? We don't know what off-t means. There is a long winding chain at the bottom of which you'll see that off-t is defined as, I think, uint64t or int64t. But regardless, it's 64 bits, right? And so how would this look in terms of the registers that we saw? fd clearly is 32 bits, so it would fit into A0. Now, POS is the second argument. It's 64 bits. And remember, I told you that 64 bits has to fit into one of the pairs, the pair registers, right? So since A0 is already used, I can't use A1 because A0, A1 is the pair. So I have to use A2 and A3 to store position. Now, once A2 and A3 have been used up, there is no free registers to store whence in, right? So that ends up in the stack. And that's where it has to be pulled up from. Okay, so now that we have something for open, right? So this has to be of type user ptrt, and this is the first argument, so it would be something like this. The second argument is just an int, so I don't have to bother about it. I just pass it as A1, right? Now it's up to you to write this function. But this is how it would look in syscall.c. Okay, so what does sysopen have to return? Sysopen has to return an integer. On success, open returns a non-negative file handle. Now, please ignore the word file handle. I think it's very bad name for this. It should be file descriptor because all the other calls actually say fd, right? Because fd stands for file descriptor. It's an integer. The file handle is the underlying file. It's in the kernel space, and the user never sees the file handle. So it's like file descriptor, file handle, file object, right? That's the abstraction. Okay, so it's supposed to return a non-negative file descriptor. Now, where does this file descriptor come from? That has to do with the file table, right? Because every process has its own file table, and that file table has basically a map of file descriptor to file handles, right? So what must be done in open is when a process calls open and gives it a path, let's assume that it's a valid path. Or if it's not a valid path, let's assume that he's given the oCreate flag, which says you're allowed to create the file if it doesn't exist, right? So let's assume it's a valid path, and so the kernel opens the file, and then it has to return an integer, right? This can be as simple as just walking down that table and figuring out which entry is free. So let's say 0, 1, 2, 3, 4 have all been opened and have entries in that file table. Now, since he's calling open on a new file, I see that 5 is free. So I return an integer, the integer 5 to him, and put the entry into that file table in position 5. Now, don't bother if you are unable to visualize all of that, because I'll give you a nice diagram at the end of this recitation explaining how the file table should look like. Okay, so that's all open does. It returns the file descriptor. Now, let's quickly go to close. What is close supposed to do? Close takes in a file descriptor and is supposed to close the file handle, right? The underlying file handle. This is a little tricky because we don't always want to close the underlying file handle. Because remember, when a process forks, what happens is it creates a new child process, but they share the same file handle. Now, if the child called close, what would happen? It would close for the parent as well, because the object is still the same, right? And that's something that should not happen. That's not allowed. Because if a child closes the file descriptor, then it ends that link between the child and parent. It's not supposed to close the file for the parent. And so you guys will have to come up with some innovative way of handling the scenario where a process forks multiple children, and they may each call close, but it should only close the entry for them. It should not close the entry of the parent or for any of the other children, right? So close is clearly a little more tricky than open was. We'll have to handle it specially. Hopefully, when I show you the diagram of the file table, it will give you some ideas as to how to handle close. Okay, so moving on to read. Now, read is pretty standard, 3 arguments, nothing of type 64 bits, so it should fit in fine, like A0, A1, and A2. The second argument is a pointer, so again, that has to be typecast to user PTRT, and we still don't know how to read and write a file. We don't even know how to open a file. We'll talk about that. But what we have to do is once we do read, however it's going to be, we just need to copy out that data, right, to the pointer that has been passed in. Now, how do we open a file or read a file or do anything with a file? So there is a folder inside the source called VFS, which is the virtual file system layer. And if you look at VFS, if you look at some of the files in VFS, you'll see that some of the functions here actually do exactly what we want. Like, for example, VFS open. What is the comment on top? Does most of the work for open, right? So you can take it as there's not much to do for open. And by open, we mean sysopen, the system call, right? So this is probably the function that we want to call when we want to open a file, because it does a lot of what we would expect, right? It checks for the modes. It has oCreate. It has oExclude. And so this is the function that we want to use to open a file. And similarly, there is a VFS close, which is probably what we want to call on sysclose. But there is no VFS read write. And well, it's up to you if you want to implement VFS read write. You're welcome to do so. But if you actually trace this chain down, you'll see that on VFS open, the one line that actually does most of the work is this. And general C nomenclature is if something is fully capital and looks like a function, it's a macro. So there is a VOP open macro that's being defined somewhere in the code, right? Where is it defined? It's defined in vnode.h. And in vnode.h, if we go right to the, okay, this is not visible. if we go right to the bottom, we see VOP open, VOP close, VOP read. Interesting, this might solve our read issue. And there is also a VOP write. But what do these macros expand to? It's a long winding chain. I don't know the answer off the top of my head, but I do know how you can get the answer. Install Eclipse, set up a project, and just put your mouse on top of this. It'll tell you what the answer is, right? But long story short, it goes to one of the SFS calls, right? The simple file system. So basically how this is structured is that the vnode stuff is like abstract. It just says it's like an interface that actual file systems have to implement. So the SFS is the actual file system, which is implementing the interfaces that the vnode exposes, like VOP read, VOP write, and all of these. Right? So that's where the call goes. And what is also interesting is I've realized that a lot of people actually don't spend time reading comments, so I'll just walk you through these. So there is this VOP open, right? What does it say? Called on each open of a file. Okay, a lot of text. I don't feel like reading it. VOP read says read data from a file to UIO. Now we don't know what a UIO is. We'll come to it. But what is important to note is this is something that actually reads data from a file, which is what we want in sysread. Right? So this is probably the function we have to call. All right, VOP write says write data or write data from UIO to file. Right? So there's a lot of talk about UIO. What is the UIO? So the UIO is found in uio.h, and it's relatively small. There are a couple of enums declared on top and the struct UIO, and each field of the UIO is actually defined. So a lot of these kind of seem very arbitrary, and we don't really have much knowledge of what these do. These comments here do help a lot. Please go through them and pay particular attention to these flags. Right? These are what are of most importance in the UIO. You don't need to understand too much of it, but these flags are something that you have to pay very close attention to because they matter a lot. And also, there is one function right at the bottom called UIOK init, right? And the comments on top says initialize a UIO suitable for I/O from a kernel buffer. Now, we don't really do anything with a kernel buffer, or we haven't come across anything that we're doing yet with a kernel buffer, because sysread says I'm giving you a pointer, and that's where I want my data to be, right? So the actual buffer is a user space buffer. So when do we use a kernel buffer? We'll use a kernel buffer when we're trying to write, because there is data coming in. Actually, even for write, you don't have to use a kernel buffer. So I'll leave it to you to figure out where we actually use a kernel buffer, because I don't know the answer. Please don't ask me. But what is important to note is that if we actually go into this function uiok init, which is defined in uio.c, we see that he sets up all these fields, right? And most of these are like generic stuff. There is an IOV passed in. He just sets uio IOV to that. There is a kbuff. This is the kernel buffer, right? And if it's a user space process, that's going to be something like user ptrt ubuff. Right? So what you're going to have to do is you're going to have to write a function that's very similar to this function and give it a different name, like uio uinit if you want, or user space init, or whatever. But as I mentioned, this seg flag, the flag is very important. So please go through the comments and figure out what that flag means, what it does, what it implies, because if you don't, you'll run into some k-assert issues later on, right? So quickly jumping back to where that flag resides. Here, so in this, we see that he sets it to uio sysspace, right? And what is uio sysspace? uio sysspace actually says kernel. Not very informative, but that's what it says. There is some explanation here as to what they mean, though. So here he explains uio seg flag and what it should be, right? And this also has, I think this block of comments actually has quite a few answers to code reading questions, in case you have not done those yet. So you have a question? The IO vector? I actually don't know. I didn't have to touch it much, so I just ignored it. Let's try and see what it is. Okay, so the IOVec has a union of IOV U base and IOV K base, right? So this is where the pointer is going to reside. So when you're reading data, when a process called sysread, he passed in this pointer, right? And that's where that pointer has to go. Because when you call the final VOP read or VOP write, you notice that you pass in two things. You pass in a vnode, which is basically the equivalent of a file or the file object as we have been referring to it. Let me quickly jump to VOP read so that I can show you. Okay, right. Okay, so VOP read takes in a VN, which is basically stands for a vnode, and a UIO, right? And the UIO has the IOVec, right? And the IOVec internally has the pointer where the data finally has to go. So when you call VOP read, he makes sure that at the end of that call, the data is where it should have been. And the IOVec stores the final destination of that. Does that make anything clear? You sure? I can try explaining it better if you want me to. Okay. Yeah. Is what used for source also? Right? Right?
Is it used in the source side also?
The UIO? Yes, depending on what you're trying to do. If you're writing, then that's where write doesn't go to user space, right? So yes, it can point to both. It just stores a pointer. So okay, so that's how we read, write, open, close. VFS open, VFS close, and where you don't have functions in the VFS layer, please go one step deeper into the VOP macros, and you should find whatever you need there, right? Now, another thing that we probably want to do is, when we're writing all these system calls, is we probably want to create our own files. I just deleted the wrong file. Oh, I didn't. Oh, I did. Okay, so when we want to create our own files, we need to make sure that these files are also compiled as part of the kernel that we are trying to build or make, right? And the way to do this is actually to go to conf.kern, which lists all the files that are going to be compiled, and add an entry there. So just go to conf.kern, save file, syscall proc syscalls.c, right? And now if I try to make this, one moment, kern compile kern conf /config assignment 2. It throws an error. It threw an error because proc syscalls.c does not exist currently, right? And this is like a definitive test that will tell you that that file is trying to be compiled, because it tried to search for the file, but the file did not exist. Now, how do you fix this error? Well, there's a very simple fix to it. I just go to kern syscall and say touch proc syscalls.c. Right? Now I go here and say bmake depend, and everything works fine because it found the file. It's empty right now, so obviously there are no compilation issues, but it worked fine. And this is how you add a new file. You don't have to bother about header files, because the way header files work is, as long as you include it somewhere, it's included in the code, right? So one of your C files has to include a header file. Yes? Touch basically just creates the file of size 0. That's all it does. See, the size of proc syscalls is 0. Now, if I were to say echo 0 into proc syscalls, and then I tried compiling, bmake depend would work fine, but bmake would probably fail. Right? So that's how you add a new file into the existing kernel. Now, read and write are very similar. The final one is Lseek. Lseek is a little tricky because Lseek, what it basically does is it doesn't really return data as such. What it does is it sets the offset inside the file. Now remember, when a process opened a file, the offset was right at the beginning of the file. Now if the process said, read from file descriptor 6 and read like 50 bytes, the offset in file descriptor 6 moves ahead by 50 bytes. This is something that you will have to save in your file table. Again, I will come to that, but remember that that's something that you have to keep track of as to what the offset into the file is. Now what Lseek does is it asks the kernel to change the offset of that file handle without actually reading or writing data. It just move the offset somewhere else, right? And so the arguments to Lseek are a file descriptor, basically pointing to the file handle whose offset has to be changed, a position, and a vens. Now the vens is like coarse grained positioning. So the vens has three types: seek set, seek current, seek end. Seek set is the beginning of the file, seek current is the current position, seek end is the end of the file, right? And for finer tuning, that's where you use the position, the off-t position. Now you can do crazy stuff. You can say seek current with a position of 0, which basically does nothing, right? You're moving 0 steps from your current position. You can do that, it's valid, but the Lseek is basically designed to give you fine tuning of where you want your offset to be, right? And we actually do some crazy things with Lseek. So there is one of the tests in your code, you can see the source code for this, it's called file only test. And if I recall correctly, the way the file only test works is it opens a new file, it writes 512 bytes, seeks to 1024 and writes another 512 bytes. And that's legitimate. It should not throw an error, right? Because the way it does that is it writes 512 bytes. So the current offset is like 512. And then says Lseek, seek end, plus, and the position is 512. So from end, seek 512 away. So although you have no data there, the file just expanded. Or the offset into the file is set somewhere else. And the next time you write, the file size has to increase to all of that. But the good news for this is there is a VOP macro that does exactly what you want as long as you pass in the parameters correctly. So I think it's called warp seek. Quickly check that. Is there a warp? Warp try seek. That should probably do what you want, I think. Okay, so that's all for the file system calls. Now we still have to talk about, there are two other things that I want to cover. One is the file table, right? I'll get to that at the end. But to get to that, I need to pull the projector up. So before that, I'll just show you something that's very useful and might help you a lot while testing. So most of the tests that we run, the source code is already available for you. And they're all found in this user test bin folder, right? And so because most of these tests actually test multiple system calls in a single test, it might not be very useful because you may have written just one of them and you want to test just that one. And so the easiest way to go about doing that is I'll give you an example. Like I'll create a test that basically tests the open system call, right? So I say mkdir open syscall test, cd space open syscall test. Because I'm very lazy, I'm going to say cp /fork test /star and put it into my current folder, right? It says omitting a directory, that's fine, I don't care about the directory, but I have two files here. I have forktest.c and makefile. So what I'm going to do is I'm going to wipe forktest.c. So I'm going to say, okay. So I say echo, see, that should have wiped it. It did. Okay, so now I go to the makefile, right? And here I see that he's creating a program called forktest. Now there is already a program called forktest, so it's going to have some conflicting issues, or one is going to overwrite the other. So I'm going to change this. I'm going to say prog is equal to open syscall test, and the source open syscall test.c, and the bin dir is still test bin. That's where I want it to go, right? I save this, I close, I open, I move my forktest.c to open syscall test.c, I open that file and I start coding. stdio.h, stlib.h, unistd.h, fcntl.h, and then int main. Go in there and say int fd equals open. Right? So I have a program now that basically does open. That's all it does. And what do I have to do now? Just return 0 so that there's no error, and bmake. Obviously I was bound to make some mistake. No errors, bmake install. And now I can actually run this test. It'll probably throw a bunch of errors because I haven't implemented the open system call. So what I can do is I quickly go to root, I say sys161 kernel, and to run this test I say p testbin open syscall test. It threw a bunch of errors because there's no sysclose, there's no sysopen, none of them, but let me try my quick hand and hit Control C as soon as I can. So p testbin open syscall test, boom. So there, unknown syscall 3 is the first message. Now, what is syscall 3? You can see it in kern include kern syscall.h. So sysexit was what was called. I wonder why. Sorry. The first syscall is actually 45, right? Not 3. So the 3 was invoked by return 0 because return 0 jumps to C library and C library calls sysexit on your behalf, right? So what is syscall 45? Sysopen. Yes. So that's how it works. And now you can write your own test to check, read, write, whatever you want. Just small pieces of testing code. And final pointer, please do not use kprintfs to debug. Syscalls are not debuggable with kprintf because when you invoke a syscall, you might get blocked and other threads might run. And this is very likely once you implement fork because there are going to be multiple threads on your system. And what happens is kprintf does not have ordering. So you will get garbled text. One kprintf might print before the other, even though that was not the order in which they actually executed. So all sorts of weird stuff will happen. So please don't use kprintfs while debugging system calls. Use GDB. And a final note is sometimes what might happen in your code is you run into these issues that says like fatal error and gives you some weird address, right? Now, you can categorize those addresses into two types. Those that are greater than 80 million or 8 million, 8 followed by 7 zeros basically, and those that are less than that. Usually if they are less than that, you will see that they are of the type 0x4 something. And if they are greater, there will be anything greater than 80 million, right? And one neat way to debug that, in case you run into those issues, is by using object dump. So you say OS161 object dump -d kernel and output all that into a .s file, right? So this is basically like assembly instructions of your whole kernel, right? So let's say there was some error somewhere in like test open. I don't even think test open exists here. So I'll just quickly jump to a random function, right? Let's say for whatever reason the address that you saw was here. Like this was the address that it threw up, right? Fatal error, unknown exception, TLB miss on store, and EPC that 8001 DFC, right? You just search in this file to where it is, and you can find out that the function associated with it is strchr or strrchr, and that's the function. So when you write your own functions, they will also have a name here. Like you write CV wait, and it gives you an address that is inside CV wait. You will see CV wait up there, and this will help you narrow down errors, right? Usually the cause for these errors are all null pointer, something like you're freeing something that you didn't explicitly kmalloc, or something was never k-malloced in the first place. So usually those are the kind of errors you'll run into, and this is a nice way to quickly identify. But you cannot apply this when you get these error messages from the autograder. That will not work, because the autograder adds its own code, right? Like the simplest case is you saw that the autograder actually had a sy4 option that you guys didn't have. I see a lot of blank faces. sy4 is the reader writer lock test, right? So it actually built a different binary than yours. So the addresses that way will not match. So you can use this for local debugging, but you can't use this while getting feedback from the autograder, right? Okay, so finally the file table. Done with this. Okay, so the file table is basically, you can think of the file table as something similar to like an array of file handles, right? It's just, it's a table, right? Where you have a notion of a key into that table, and you have values, right? And the values are basically the file handle. The key is the file descriptor. So what the kernel does is, or you can also think of it like lockers, right? You have these lockers in the bank or whatever, that's the file table. And when a process wants to open a file, he requests for one of the keys. And the kernel goes and checks which locker is free and hands over the key and puts the file handle there, right? So the next time the kernel wants to do an operation on that file, he just gives the key, and the kernel can figure out which handle it is, right? So there are some things though that are important that need to be in the file handle. Oh God, these both are bad. I don't think you can even see. Marker for now. Does anyone have a marker? Thank you. Okay, so it's a very bad table, but let's just assume this is the file table that we have, right? Few things to note. Entries 0, 1, and 2 in every file table is special because they stand for standard input, standard output, and standard error, right? And so there's a special way you have to handle these file descriptors. It's there in the description of the assignment. What you have to do is you have to open this special device called con, basically stands for console, and you have to open them with special privileges. Clearly read, and std in is typing in stuff, std out is giving back stuff, right? So they kind of oppose each other. I leave it to you to figure out which should be opened with read mode and which should be opened with write. Anyway, so 0, 1, and 2 are kind of taken already. You playing tricks on me? What? This is yours. Okay, so okay, so that's 0, right? Okay, so 0, 1, 2 are special. So let's just ignore what they are. So these are indices. These don't actually exist in the file table, right? They are what we use to identify the file handle in the file table. So your file table should not actually contain these indices. So what the file table should contain is what goes into here, right? And we need to figure out what goes into here. The first obvious entry in the file table itself is the file object, right? So don't go on creating file objects. just like, please don't go creating struct process. We don't need a struct process. In OS 161, process is equivalent to thread. So don't take it as like your life's mission or the assignment's mission to create struct process. It's not needed. So what is the notion of file in OS 161? It's the V node. The V node is basically what we refer to as the file object. So that needs to go in here. And think about it. So when a process forks, remember that the child and the parent actually share the file handle, right? Which means they both have the file open, which means they both can read or write. And so you don't want, so when one process is trying to say fatal error, you don't want the other one saying everything okay, right in between. So you're going to see something like F, E, V, A, stuff like that. So you want some synchronization on a file, right? So there needs to be some synchronization that you need to use, which I will term as sync. Please don't use reader writer locks for this. That's not required. I think you can actually do it, but please don't. So that's the synchronization part of it. And then, as I mentioned earlier, you need to store offset, right? That's something that you need to maintain. So that's the third. And remember, we also need to keep track of, so what permissions the file was opened with, because a file that was opened with read permission should not be written to, all right? Or if someone was trying to write to it, he should get E bad F, which is the corresponding error. So permissions. And there is one last entry of significant importance, which I covered a little bit before, which is when a process forks, the file handle is shared. What if the child says close on that file descriptor? The file handle will get closed, right? Which means because they share it, it will close for the parent as well. But that's wrong. That should not happen. So the way we do this is, the easy way to do this is by pairing up opens and close. For every open, there should be one close, right? But fork does not actually call open, right? And so the one way of handling this, which is very neat and actually very simple to do so, is by maintaining what is called a reference count, right? So every time we actually create a duplicate or a copy, what we need to do is increment the reference count, right? So when we call fork, the table has to be copied. So all these file handle entries will actually be pointed to by the child's file table as well. But while doing so, when we create the copy, for each of these file handles, we'll increment the reference count, right? And so when sysclose is being called, we can do a quick test. Is the reference count 0? Because if it isn't, then someone somewhere has access to this file. And so I shouldn't call like VFS close on it, right? So it allows you to easily handle, like, there's another system called dup2, which I didn't cover, which is also a file system call, but what it does is it closes one of the file handles and makes it point to something else, right? So it actually makes the handling of dup2 and fork very, very easy for you. Dup2, fork, and close, right? So with reference count, the only thing you need to check for is whether the count of this handle is actually 0. If it is, then there needs to be some special handling. If it isn't, well, then clearly it's like a child somewhere that's actually using this. And so all you need to do is set that whole entry to null. Like clear whatever you want to clear. Actually, none of these should be cleared. So just decrement the reference count, set it to null, right? Once you do that, that child has no longer has access to this file or the file handle. So that's all you need to do. And next week, we'll be handling the process system calls. Please don't wait until recitations to start. It's going to be too late. Please come by office hours. We hold like 27 odd office hours a week. Find some time, come there and get help.